Welcome. Last time we looked at the definition of partial derivatives. Now let's see how to calculate them. The idea is based on the concept I mentioned last time. If I'm differentiating with respect to some variable, I just pretend that all others are actually constant. All other variables are constant. And then apply the rules of differentiation we saw in chapters 11 and 12. So let's start by looking at some simple example. The simplest case is a polynomial, which is what we have in this example. The function is x cubed minus 3xy plus y squared. To find the partial derivative with respect to x, so f sub x, I pretend that y is a constant. Since I have a sum of terms, I go term by term. The first term is x cubed. If x is the variable, the derivative of x cubed is 3x squared. The second term, I have both x and y. I think of it as x times 3y. Or if you include the negative, you think of it as x times negative 3y. So when I'm differentiating with respect to x, I pretend that y is a constant. So negative 3y is a constant factor. So I have a constant factor negative 3y times x. By the rules from chapter 11, the derivative is the constant factor negative 3y times the derivative of x. Derivative of x is 1. So I get negative 3y times 1. In the last term, I have just plus y squared. If y is constant, so is y squared. And derivative of a constant term is 0, so I get plus 0. So the partial derivative of this function with respect to x is just 3x squared minus 3y. What about the partial derivative with respect to y? In the first term, I have x cubed. If I'm differentiating with respect to y, I treat x as if it's a constant. So I treat x cubed as if it's a constant. Derivative of a constant term is 0. In the second term, I have minus 3x times y. If x is constant, minus 3x is constant. So I have the constant factor minus 3x times y. Derivative of y is 1. So I get minus 3y times 1. In the last term, I have plus y squared. I have just y, so I differentiate as usual. Derivative of y squared with respect to y is 2y. So the partial with respect to y is minus 3x plus 2y. Next, let's do an example which involves both a fraction and a square root. Since I have a fraction, I have to use the quotient rule, and I change the square root to a fractional exponent. Of course, you can also bring that to the numerator and then use the product rule. We will just leave it like this. I have to explain the notation a little bit. The function is called h. Here I have h sub x, which means a partial derivative with respect to x. So I treat y as if it's a constant. And this notation, just like in the one variable case, means first find the partial derivative, then evaluate when first variable x is 3, second variable y is 4. Let's do the partial derivative as it is first. As I said, I'm going to use the quotient rule. I will get a fraction for the derivative as well. In the numerator, first I have derivative of the original function's numerator. In the numerator here I have x plus y. I'm differentiating with respect to x, so I'm going to treat y as if it's a constant. In the first term I have x, derivative with respect to x is 1. In the second term I don't have x, I just have y. I'm treating it as a constant, and derivative of a constant term is 0. So derivative of the numerator with respect to x is just 1 plus 0 times the original function's denominator minus the original function's numerator x plus y times the derivative of its denominator. So I have to find the partial derivative of the quantity x squared plus y squared to the power 1/2 with respect to x. From chapter 10, we know that we have to use the power rule in combination with the chain rule. First, I differentiate for this exponent 1/2. So I use the power rule for that. I get 1/2 times what's inside the parenthesis and then to the power negative 1/2 times derivative of the inside. I am differentiating with respect to x, so I treat y as if it's a constant. The first term I have x squared, the derivative with respect to x is 2x. In the second term I have y squared. Since I'm treating y as if it's a constant, y squared is also treated like a constant. Derivative of a constant term is 0. So I get 2x plus 0. And finally in the denominator I get the square of the original function's denominator. Then I can evaluate this at the point 3, 4 by substituting 3 for x and 4 for y, and then simplifying this, which gives me 0.032. Another way to do this is, since we are treating y as a constant, y is just 4. So plug in 4 for y, a function of just x, differentiate with respect to x. Later on, we'll be doing a lot of partial derivatives in general, so it's better that we do it this way as a preparation for that.